Okay, welcome to our next unit. We're going to be going through some different material this unit. We're going to look at not only qualitatively describing what's going on, but this is our first unit where we're going to have to start to quantify and measure and calculate some different values about chemical reactions. So this unit is going to look at changes in energy. So it's going to look at what happens when a reaction actually occurs. Why does it get warmer? Why does it get colder? What happens to that energy? How is it released? And we're going to look at rates of reactions as well. So we're going to try and get some understanding of how reactions are governed by the properties like their surface area or the temperature of the room or the pressure. So we're going to look at things that can affect the rates of a reaction and learn a little bit about how we could speed reactions up, we could slow reactions down and get some control over that, as well as we'll look at something called a reaction mechanism and collision theory, so we can understand the things that actually govern how fast a reaction goes. Okay, so a little different unit. This will be new stuff for everyone. One of the first things we want to do is take a look at a reaction and try and describe what actually happens during a chemical reaction. And in this first section of the unit, we're going to focus on the changes in energy that happen. So if you take a look at this graphic, we have energy on the side and kind of a reaction happening, progress of that reaction as it goes across the bottom. And just to put this together, you can see that we're going to react some hydrogen gas with some oxygen gas, and we're going to make water. So this is a combustion reaction. We've seen this before in the lab when we collect the correct amounts of hydrogen and oxygen, and then we light them. There is a rather explosive release of energy. So not only is there energy released if you do this right, it's quite explosive. Its rate is quite fast. But on this graph, what we're trying to do is show what happened to the energy during that explosion. So an explosion gives off energy. It releases that energy into the surroundings. And we've seen that as light and heat. And that energy is released and lost from the molecules that were involved in the chemical reaction. So here on our graph, we see that we have H2 and O2. And if we could represent their relative amount of energy on the graph, that's what this line represents. All of the energy that's stored in the H2 and O2 molecules. As the reaction proceeds, all of that energy is released, not all of it, but some of that energy is released as those atoms rearrange, they make new bonds, and they end up making H2O molecules. And that energy is released, and then at the end, we have these products down here that have less energy than the reactants that started. And that has to happen. You can't have energy released from a reaction without the reactants and products losing energy as a result. Energy is always conserved. It has to go or come from somewhere. And so this energy is lost in the explosion, and then our products have less energy than the reactants that we started with. Now you'll notice I have no numbers on the scale. This is just kind of a qualitative look at what's happening. But we'll get more into the numbers and things as we move along. Right? And basically, we're going to try and take a look at two different kinds of reactions. We'll look at physical changes, changes of state or dissolving. Those things have energy changes related with them as well, right? We have to heat up an ice cube to make it melt. So we can do some energy calculations to figure out how much energy it would take to melt or to boil a certain amount of water. Or we can do a chemical change like we've done here and calculate whether that chemical change will generate energy or lose energy for us. And so the energy changes in a reaction are the result of those two things happening. And we can actually do have reactions that the products end up with more energy than the reactants. And so there's a difference there of how things are happening. And we'll take a look at those reactions so you can get a handle on both kinds. And reactions that release energy are probably more common that we've done before, but there are lots and lots of reactions that actually absorb energy and end up with products that have more energy than the reactants did. And if you think even just simply of photosynthesis. If you've done some biology and some grade 10 science, you know that photosynthesis takes water and CO2. So those are reactants in photosynthesis, and they're down here at the bottom of our graph. They add energy in the form of sunlight, and they make sugar and oxygen. And so that is an opposite to what I just drew with the hydrogen. That's a reaction where the system actually absorbs energy, and the products have more energy than the reactants did. Okay, so when we're talking about energy, this is where it gets a little bit tricky. We are going to look at the molecules and the atoms and things in the compound. And the energy that we're talking about is the energy that's associated with those chemical bonds. So if we take a look at a hydrogen molecule, it's two hydrogen atoms joined together with a sigma bond. There's a fair bit of energy stored in this bond, right? And then if we take a look at the oxygen, same thing. It's an oxygen atom with a sigma bond and a pi bond, so they're double bonded together. And there's a lot of energy stored within that bond. And that energy is what we're trying to measure, the changes. So when we take those two bonds and we go through a chemical reaction which rearranges them, and then we end up making a water molecule. So water, we had to break the hydrogen bonds, and then we've reformed that and added bonds to an existing oxygen. And so that process of bond breaking, so over on this side we have to break these bonds, and on this side we have to make these bonds. That's what we're trying to measure the energy changes. Right? We're trying to see what the difference is from the left side to the right side of the reaction. There's a number of ways we can do that as we go through. Now, what we are not going to be able to do is kind of measure an absolute number. If you think of an atom, atoms in the molecule, well, there's a positive center in an atom, and then there are negative electrons. I'll just use a Bohr diagram for now, moving around that atom. And those things have energy between them. There's energy in the electron moving. There's energy stored in the electron-proton attraction. If we have more than one orbit, so we'll put two electrons in this first orbit and one in this next one, then these have repulsive forces acting on each other. And then if we build a bond and we bring another atom into the picture, then there is repulsion between the two protons, attraction between this proton and these electrons, and then more repulsion between the electrons of this atom and the electrons of that atom. So there's all kinds of interactions going on in here. Don't forget also these atoms and molecules are all moving. So they're vibrating, they're rotating, they're translating, and all of that is energy as well. So molecules and atoms have an incredible amount of energy stored in a number of different ways. We can't possibly hope to add this all up and come up with what would be like an absolute number of energy. So instead of that, we take a look at what happens when we change these molecules. So if you just think of the number, the millions and millions of atoms that are being involved in these changes, there's no way to take all of the repulsions, all of the attractions, all of the kinetic energy of the things moving around, add it up and figure out exactly how much energy you have. So what we do is we're going to look at something called a change in energy. So a little triangle means delta, or change in, and we're going to take a look at the change in energy. This is something we can fairly easily measure. We can do that by taking temperature measurements of our surroundings and see how those temperatures change. Imagine when we blew up the hydrogen, things would have got hotter. We can use this temperature change to calculate out a change in energy. So we won't know exactly how much energy is in the system, but we will be able to tell how much the system has gained energy if it heated up, or how much it lost energy if it cooled down. But the actual absolute amount of energy is not something that we're going to be able to calculate. So you need to remember that there's a huge amount of chemical potential energy that we're not accounting for, and that we're only looking at what happens during the changes. So we take a look at two examples just to get some practice drawing these diagrams. When we draw the diagram, basically what we're going to use is just an axis. So we draw an X and a Y axis. And we won't put a 0 point on here. Like we said, we don't know where absolute amount of zero energy is going to be. We're just trying to represent what's going on inside the reaction. Now, when we look at this reaction, we see we've got methane, CH4 plus oxygen. So we're going to do a combustion reaction. So that should release energy. That's why we burn fuels, and producing CO2, H2O, and then we've added in a new term here. We can add in a term that says where the energy is. In this case, we're just adding in the heat energy. Now, there could be light energy and sound energy, but we're just going to encompass all of that in this term heat. So that when we look at this reaction, if we were to draw where the reactants were when we started, the reactants would be up here. And we just draw a horizontal line like that. And because heat is a product, what that tells us then is that there's going to be heat coming off of this reaction. Sorry, that's better. Heat's going to be coming off of this reaction, and we're going to lose that heat out of the atoms and the molecules that are involved in what we're talking about. So if that energy is lost to the system of atoms and molecules, then that means when we go back and take a look at energy, our products should have less energy than our reactants did. So we draw another horizontal line down here, and that represents our products. And then we can join those two lines together to get a graph that looks something like this. Right? And so this drop here is the change in heat energy that we've just experienced. And we've lost that heat energy out to the system. So we would put CH4 up here, O2 here, CO2 down here, and H2O down here. Right? And then this is just energy. You can think of it as chemical potential energy on the side. So we're just trying to illustrate that change, and eventually we'll quantify this amount of heat. We'll figure out what that is. That's our kind of our goal in the first part of the unit, and then we'll express that number in kilojoules of energy, so we know exactly how much energy was lost or gained by our system. Okay. Now, if we look at another example, this example uses ammonium chloride and barium hydroxide. And what happens in this example is the opposite of what we just looked at. So when we have this example, I haven't put the heat term in there yet, but if we drew a graph, again, we just do a y-axis, x-axis. This one is actually does the opposite. This reaction pulls energy out of the surroundings and adds it into these molecules as they rearrange. So that means that heat comes over here, and heat is actually one of our reactants. We need heat to make this happen. So on our graph, heat is going to be pulled in to this reaction. It's going to come from the air. It's going to come from the water if it's happening inside an aqueous solution. But heat is going to be pulled out of the surroundings and added into our system. And so when we draw the system this time, what we have is our reactants are down here. They absorb energy, and then when done, they have more energy than what we started with. Okay? And so we've got the opposite of what we were just looking at. So the NH4Cl goes here, the BaOH2 goes here, the BaCl2 goes up here, and the NH3 goes here. And then because heat was absorbed into this system, the products have more energy than the reactants originally did. Okay? Now we have names to identify those two kinds of reactions. This reaction is called an endothermic reaction. Endothermic because it pulls energy or heat energy into itself. Endo referring to inside. And then just to go back to the past screen, this one was called exothermic because it loses energy out of the system. Energy moves out of the molecules and into the surroundings. So we have two kinds of graphs that we're going to be looking at, exothermic reactions and endothermic reactions. So what we want to do next then is take a look at those energy graphs and learn how to calculate how much energy is actually lost or gained by the system being the reaction that's taking place. So we can do that by looking at temperature changes. And changes in temperature actually can be translated into changes in energy. So if you remember from last year in grade 11, we took a look at temperature. In particular, we looked at the Kelvin scale, but the Celsius scale will work as well here. Temperature is actually a measure of the average kinetic energy. So how much are those particles moving and how much are they translating, rotating, and vibrating? So remember, particles do all of those things, and measuring the temperature gives us some idea of what those particles are doing. And if we increase the amount of energy in a system of particles, then we know the temperature goes up. And if we decrease the amount of energy in a system of particles, then we know the temperature goes down. So there's a connection between kinetic energy and temperature. And so we can use that in order to find a way to measure energy. We don't have any heatometers. We don't have any way of measuring heat directly, but we can measure it by measuring changes in temperature, which were caused by changes in energy. Okay, so we need a formula for that. But here's our heat thermochemistry formula. So we're going to have something called Q, and Q is just a quantity of heat. So we're just going to calculate out a quantity of heat, and that's why we use a Q for the symbol. And that can be measured in many different things, calories. Well, I won't get into all different units because there's a bunch of different non-metric units, but that quantity of heat is going to be measured in joules, and joules are fairly small, so most often we end up using kilojoules to tell how much heat we've got. Mass is simply going to be measured in grams. T can be in different units. We're going to use this formula in such a way that we can use T as in degrees Celsius. And there's that triangle again. So this is not just the temperature, but the change in temperature as a reaction's happening. And then finally, C is called the specific heat capacity. Specific heat capacity. And that's a number that you're going to be able to look up. You'll have a table of data that tells you what the value is for different materials. And it is a number that tells us how much heat does it take in order to warm something up by 1 degree Celsius. So it's joules per gram degree Celsius. So how much heat would it take to warm up 1 gram of water by 1 degree Celsius? How much heat would it take to warm up 1 gram of iron by 1 degree Celsius? So if we just flip forward here, I'll show you the graph, show you the table that what that looks like. And we can look up this data. And so you can see water takes 4.18 joules per gram degree Celsius. So for every gram of water you want to change its temperature by 1 degree, you have to come up with just over 4 joules of energy. If you go down and look at iron, iron only takes 0.4 joules of energy for every gram increase of 1 degree. And then you can look up almost any material and find out what its specific heat capacity is. Okay, so that's a number that you'll have to look up. You can Google it. You can use a table like this one. There's tables in the textbook that give you these numbers, and that's how we're going to get those numbers for specific heat capacity. So it's an experimental number that someone else has figured out that we're going to make use of. Okay, and then finally, the other little part of this is to get delta T. We're going to take whatever temperature our system ends up at the end. We're going to call that T final. And we're going to subtract off whatever the temperature was at the beginning. So we're going to use this change in temperature, run that backwards into our formula so that we have a change in heat. And then we'll be able to tell what's happening in the surroundings around our chemical reaction. Okay. Now when we calculate Q, Q actually has 2 parts. It has a magnitude, meaning how much energy. So the magnitude would be 232 kilojoules, just telling us how much energy is involved. And secondly, it has a sign. So those of you who've done physics, you know, sometimes we use negatives and positives to show which direction things are happening in. If you have a Q that ends up with a negative value, so like negative 185 kilojoules, that means that the surroundings lost 185 kilojoules of energy and they got colder. If we get a Q value that is positive, so positive 232 kilojoules, that means that the surroundings gained energy and the surroundings got warmer. So a negative and a positive just tells us whether the surroundings got cooler. So a negative is the surroundings getting cooler, cooler surroundings. And a positive indicates that at the end we should have warmer surroundings. So that's how we're using the negative and positive. We're just assigning those to be those directions within our chemical reaction. Okay? Okay, so that gives you a fair number of things to think about. And before we get on and actually try and do a calculation, I'll do this in the next video. We'll do a calculation and show you how we calculate how much energy is involved. You want to take some time to read the textbook and get some ideas about energy changes and get a better understanding of what we mean by Q and changes of temperature and those kinds of things. And look at a few of the graphs in the textbook that show you how energies are changing. So like an exothermic and an endothermic graph. So this is in the exothermic graph. Make sure that you take a look at those and kind of understand where the heat is coming from, how the reactants and products are changing. And then in the next video, we'll get into calculating out how much energy is involved in those changes. And so that's where we'll pick it up next.